like I said, we're going to use Riemann sums to find the true area under a curve of some function along a given interval. So today I want to do some review on sigma notation, how I can express a sum using sigma notation. Expressed in summation notation or sigma notation. This is the Greek letter capital sigma. Looks kind of like an E. We use sigma notation to represent a sum. The lower bound and upper bound in this particular sum to 6. For all the first term, a sub 1, is found by plugging in 1 for my index, this I here. 3 times 1 is 3, plus 2 is 5. A sub 2, the next term in that sequence is found by plugging in 2, obviously, right? 3 times 2 is 6, plus 2 is 8. Add all those up, and we'll have that summation. You guys did, I think, geometric sequences, arithmetic sequences, infinite summations, maybe in algebra 2. So just some review on summation notation, different sums and sequence formulas today. Let's see, add this all together. 13, 24, given summation notation, given a sigma notation expression, the answer we're looking for here is what that sum evaluated to be. Might see problems like that. Write out all the different terms of the sequence, take the sum. Does that make sense? You also might see questions like this. Write the sum below using sigma notation. Given the three over 7 plus 4 over 7 plus 5 over 7 plus 6 over 7. How could I use sigma notation to write that sum? As you're writing term, the numerator, right? The denominator is always. So, how many different terms do you have to write? How many different terms are there in this? What are some different summation notations, some notations that you guys have written?
Seven plus i's over 7.
2 over 7 plus I over 7. Sure. That would just be the same as I plus 2 over 7. Let's just write it as one ratio, maybe. Same thing, right? Since you had a common denominator of 7. When I equals 1, 1 plus 2 is 3, 3 over 7. The next integer, when I equals 2, 2 plus 2 is 4 over 7, 4 sevenths. All the way up to an I value of 4. 4 plus 2 is 6, 6 sevenths is the last term of the sequence. Did somebody have something different? Interesting. Nora's hypothesis is that you can use different starting values for your lower bound. Absolutely. You don't have to start with 1. 1's typically the starting number because I start with the first term of the sequence, but there's nothing that says that you have to. What if I change the lower bound? Could I write a different formula for this same summation? What would it be? Do you have a, sorry, go ahead, Dustin.
Yeah, but I equals 3 is a lower bound.
2, 1.
Then 6 on the upper bound. Just have to be 1/7 I. Or I over 7.
Sure. Starting from an index of 3, starting from a lower bound of 3, I is 3, 3 sevenths. Go to the next integer, I equals 4, 4 sevenths, add that on. The next integer, I equals 5, 5 over 7, add that on. So, those are probably the two that I would think of. Nothing says you can't start with different numbers besides 1 and 3. What if I start with 4? If I start with 4, I have to have an upper bound of 7. And what's going to go on top? All of those are the same. All of those express the same sequence, the same summation. Questions there? All right, let's do this then. Some useful summation properties and summation formulas for us to familiarize ourselves with on the middle part of the board. Summation properties. The first one is kind of like a familiar constant multiple rule. Similar to what you've seen in derivative. The summation from I equals 1 to n of constant k times I can just factor that constant out. Take the k, multiply it out in front of the summation. The summation from I equals 1 to n of k times I is equal to, pull the k out as a constant, I equals 1 to n of only I left. Similar to a constant multiple rule. Another summation property to keep in mind is kind of like the sum or difference rule that you've seen before with respect to derivative formulas. The summation of multiple terms separated by a sum or difference, a plus or minus, can be written as two different summations with a plus or minus. The summation from I equals 1 to n of quantity a sub I plus or minus b sub I is the summation from I equals 1 to n of a sub I plus or minus a different summation for the next term from I equals 1 to n of b sub I. Okay, let's try this. Some summation formulas. how can I evaluate some of these sums without having to write them all out? Right? I don't want to sit here and write out 20 different terms if I have a summation that goes all the way up to 20. So what are some formulas that would be helpful in evaluating some of these different sums? So the summation from I equals 1 to n of some constant is that constant times n. N represents how many times that constant was added together. If n is 5, I have that constant c added with itself 5 times in total, right? In general. So in that particular case, I have c added together 5 times. The total sum would be 5 times c. Another way here, I equals 1 to 4 of 6. How many 6s get added together there? So it's 6 plus 6 plus 6 plus 6. I have 4 total 6s added together. I have 6 4 different times. That's just 4 times 6 are 24. N represents how many different terms there are. They're all the same constant. So the total summation is that constant multiplied by how many times you've added it together. The next one is the summation of integers. The summation from I equals 1 to n of I. In terms of n, that's given of n times n plus 1 over 2. The summation of the first n integers would be n times n plus 1 over 2. So for example, the summation from I equals 1 to 5 would be 1 plus 2 plus, forget the index. The summation from I equals 1 to 5 of I is 1 plus 2 plus 3 plus 4 plus 5. I'm adding up the first 5 integers. 1 plus 2 plus 3 plus 4 plus 5. That would be, let's see here, 3, 6, 10, 15. Using this summation notation formula here, I can take 5 times 5 plus 1 over 2. 5 times 6 would be 30. Divided by 2 is the same 15 I got. The sum of the first n integers is given by n times n plus 1. This actually has kind of a unique story behind it. Because this would have been back in the 1800s or so. There was a young mathematician by the name of Carl Friedrich Gauss. He would go on to be one of the most influential mathematicians of all time. And when he was in primary school and elementary school in Germany, he got in trouble for talking out of turn in class. And so as a punishment, his teacher made him add up the first 100 numbers. 1 plus 2 plus 3 plus 4 plus 5 plus 6, and so on, all the way up to 100. Add all those up, give me your final answer as a punishment, right? He had that done in about 30 seconds. His shortcut that he found was, all right, if we're going to do the first 100 integers, I have 1 plus 2 plus 3 plus 4 plus all the way up to 100, right? Now just reverse it. Instead of starting at 1 and counting up, let's start at 100 and count down. If I add these together vertically, what do each of these columns add up to? 101. 101 plus 101 plus 101 plus 101, all the way down the line, right? How many different 101s is that? How many different 101s have I added together? 100 of them. So what I've done so far is I've taken one sequence from 1 to 100. I've taken one sequence from 100 down to 1. I have 101s altogether, right? But isn't that twice as big as it should have been? Because I did one sequence and then added on the same thing again. I want just one of those sequences, right? So let's just cut that in half. Within about 30 seconds, he had the final answer of, let's see, that would be 10,100 divided by 2, which is what, 5,050? In about, what, 9 or 10 years old, he had that figured out. The summation of the first 100 integers is 100 times 101 divided by 2. So,
Yeah. Oh, I was gonna wait for you to have a break.
it's going to be about another 15, 20 minutes.
Oh, perfect.
Okay.
They can be a break. Yeah, I like their.
All right, next up. I don't have a good proof for these. You could have certainly looked them up. I don't know it off the top of my head. But I have the summation formulas for the first n perfect squares and the first n perfect cubes. Good formulas to memorize. These are going to be helpful as we move throughout this next couple of different units. The summation from I equals 1 to n of I squared, all the perfect squares, so like 1 squared plus 2 squared plus 3 squared plus 4 squared and so on, would be n times n plus 1 times 2n plus 1 divided by 6. This summation would look like, for example, I equals 1 to 4, 1 squared, I always do that, of I squared is 1 squared plus 2 squared plus 3 squared plus 4 squared. I'm summing the first 4 perfect squares. In general, the first n perfect squares would be n times n plus 1 times 2n plus 1 over 6. For perfect cubes, for I cubed, what is the summation formula for the first n perfect cubes? The summation from I equals 1 to n of I cubed is given as n squared times quantity n plus 1 squared over 4. For example, if you have the summation of I equals 1 to 5 of I cubed, that's the first 5 perfect cubes. 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. Rather than sitting here writing this all out, I could just plug in 5. 5 squared times 6 squared divided by 4. Rather than sitting down and doing this perfect square summation, I can just plug in 4 for n. 4 times 5 times 9 divided by 6. All right, once again, those are good ones to memorize. We'll get familiar with them, but please work towards memorizing those summation formulas. Let's use them in practice. For our summation, our signal notation, our summation from I equals 1 to n of 4i squared plus 3i, write as a summation function s of n, and evaluate for n equals 30. I want to write a given function in terms of n for any upper bound that I want. The summation from I equals 1 to any n value that I want, and then evaluate for this sum when n is 30.
I hope
I can't point worksheet for Tate to do. I got the midpoint distance worksheet, but there was no coordinate proof worksheet.
Oh, okay.
attached
Because
to that.
if you go
'Cause the
onto
thing
that document,
Yeah,
let me
I was on.
explain what that is. There were, I think, about a half a dozen different geometric figures that you had to prove
Okay.
were rectangles, squares,
Oh,
trapezoids,
is that what you meant
parallelograms.
down below?
Yeah.
You said pick 4?
Yep.
And that's for that assignment?
So the coordinate geometry. Pick any 4 of the 6 figures below. Prove each is the desired shape or the described shape. So
Okay, so
if you
do
open
those.
up this
Click
shape, prove that this is a square.
Okay. So that's what we do. All right. I got them working on
Square is a
midpoint one.
parallelogram with 4 right angles and 4 equal sides. So show that the opposite sides are parallel. The 4 angles are 90 degrees,
Mhm.
and then all 4 sides are the same length. for example.
And that, he's doing the midpoint worksheet and then this worksheet.
Okay.
And then
Yeah.
Whatever
Any 4 of the 6. Any 4 of those half dozen. That's all good.
Thanks.
Mm-hmm. Okay, where was I? All right, let's first work with the sum. Let's write a summation function first and then evaluate for n equals 30. The summation from I equals 1 to n of 4i squared plus 3i. Summation property says I can write that as 2 different sums first. So the summation from I equals 1 to n of 4i squared plus the summation from I equals 1 to n of 3i. What can I do with the 4 and the 3? Mark the front. I can take these constants that are being multiplied by I and I squared and factor them out in front of the summation. So let's write this as 4 times the summation from I equals 1 to n of I squared plus 3 times the summation from I equals 1 to n of I. My whole purpose was to get to a point where I can use these summation formulas to the left. I have a defined summation formula for the summation of I squared, the first n perfect squares. I also have another summation formula, the summation from I equals 1 to n, for the first n integers. So let's replace those summations with what they're equal to in terms of n. I'm going to replace the summation from I equals 1 to n of I with this expression here. Does that make sense? I'm going to replace the summation for the perfect squares from I equals 1 to n of I squared with this expression here. So this should be 4 times n plus 1, 2n plus 1 over 6. Plus 3 times n quantity n plus 1. 2. Let's start simplifying. Multiply 4 times n. While I'm here, I might as well multiply n plus 1 times 2n plus 1. N times 2n is 2n squared. N times 1 is n. 2n times 1 is another 2n, so altogether that's 3n. 1 times 1 is 1. Trying to simplify this expression for our function that's going to be in terms of n. Let's do the same thing here. 3n times n plus 1, so 3n times n is 3n squared. 3n times 1 is 3n over 2. All right, let's see. I'm going to multiply the 4n times these terms. 4n times 2n squared makes 8n cubed. 4n times 3n would be 12n squared. 4n times 1 is 4n over 6. Eventually, I'm going to want to add these together. In order for me to add them together, what do they have to have first? What do these two ratios have to have before I can add them up? So what's the common denominator between 6 and 2? 6. This one's got it, this one doesn't. How do I make this have a 6 in here? Multiply by 3 to top and bottom, right? So take the top and triple it, takes the bottom and triple it. 3 times 3n squared is 6n squared. 3n times 3 would be, wait, no, I'm sorry, 9n squared. I got to triple it. just doubling 9n squared plus 9n over 6. Let's add them all up. 8n cubed, 12 and 9n squared make 21n squared. 4 and 9n make 13n all over 6. Can I reduce anything down? 8, 21, and 13 and 6. No, 13 is prime, so that's not going to work. Here is my summation formula, S of n. For any upper bound n, I can evaluate that sum using this function here. What do I want to evaluate it for? 30. I want to know what this is. The summation from I equals 1 to 30 of 4i squared plus 3i. Could you all sit here and do 4 times 1 squared plus 3 times 1? 4 times 2 squared plus 3 times 2. All the way up to 30 and add them all together? Yeah. Isn't this a lot easier now? I can plug in whatever I want to. Say it was 40. Then you plug in. If I had a 40 here, what would I plug in? 40. If I had a 50 here, what would I plug in? 50. I can plug in any upper bound that I want. I have an expression for any sum given this index here. So S of 30 would be 8 times 30 cubed plus 21 times 30 squared plus 13 times 30 over 6. Okay, so obviously I need a calculator. Eight times 30 cubed plus 21 times 30 squared plus 13 times 30 all over 6. 39,200. Why don't you guys grab your laptops? Get onto Desmos. Get onto the graphing version of Desmos, please. So I'll go back to the Desmos menu and go to desmos.com, open up the graphing function. Where's my calculator? Oh, right in front of me. Cool. Get on to the graphing calculator. Let me share my screen here. Sorry, guys. Pardon me. So y'all online can see what I'm doing. Desmos has a summation calculator feature that I'd like to show you. If you open up the keypad in the lower left corner, I believe it's under the miscellaneous menu, and this sigma feature here. They use n instead of I, but it works the same. We're just going to type in n equals 1 to 30. of quantity, make sure you put it as a quantity, 4n squared plus 3n. Everyone find that okay? On Desmos, the graphing calculator is the only calculator that has the summation function featured. The scientific calculator does not. So you have to go to the graphing window and just type it into the input bar on the left. How are we feeling? Doing all right? Okay. Could you please go to Schoology then? Let's talk about the rest of the week, today and tomorrow. I will be out of the building tomorrow for a funeral. I'll have a short video for you to watch and some practice to work on. Since we're going to pull up the practice right now, and I have everyone here, let's just talk about where I want you to get to by the end of class tomorrow, okay? So area under a curve, unit 4, standard 17 Riemann sums, using Riemann sums to find the area under a curve, the exact area, not an approximation. After today's lesson, you should be good through the first 7. If you wanted to get started today, the first 7 are available. After tomorrow's lecture, I'll have through, what is that, 12, basically the bottom of this first page, through the first dozen after class tomorrow, by the end of the week. Does that sound fair? Next week, we're going to get into Riemann sums starting on Monday. How could I use summation to find the exact area under the curve on a given interval? For example, how could I use summation to find the area under y equals x squared plus 2 on the interval from 0 to 1? That's our goal. Use summation and summation formulas to find the area under a curve, rather than some approximation using geometric figures like rectangles and trapezoids. Well, online soldiers, how we doing, guys?
I'm doing good.